last time, what did we do? We did kind of this convex optimization kind of crash course overview. Talked about convex sets and stuff. Hopefully that was pretty intuitive and everyone, yeah, we had some good questions about this. That was good. That's sort of bread and butter stuff. This isn't really a course on convex optimization. It's a controls course. We use that stuff. If you're into that stuff though, highly recommend if you're going to like go further in this, general area to check out like there's full semester courses on convex optimization. Highly recommend taking one of those at some point in your life if like you're into this kind of stuff and you're going to do more optimization. That's sort of really important stuff. If you want to self-study that stuff, I highly recommend Stephen Boyd's books and lectures that are online. It's called Convex Optimization or CVX 101. That stuff's awesome. Check that stuff out if you're not going to take a course, but you want to learn more. Boyd, anything Stephen Boyd, basically, the book and the YouTube lectures and stuff. Really good. And then we did Convex MPC. And, I would argue what you should think about that as like LQR plus constraints. If you're in like a scenario where you can get away with linear models, but you need to handle some like obstacle avoidance, safety, torque limit kind of stuff, that's pretty much the answer. Okay, so today I want to just finish up by kind of like giving you a handful of examples of convex MPC problems or convex, like cool applications where convex MPC is used. So we'll talk a little bit about that. We're going to get more into some of these later in the class as we do like kind of case studies, but I just want to give you a little flavor of just to like drive home how useful this stuff is and how powerful it is. And then from there, we're going to start talking about nonlinear stuff. So far, right, we've been really harping on the linear models. These are really useful and really powerful. So you should really like honestly use linear models if you can get away with it. I mean, get away with it a lot. So like that's a good idea as a starting point. But life is nonlinear, so sometimes we gotta do this stuff. So we'll talk a little bit. Next up is nonlinear trajectory optimization. So this is really kind of what happens when you have to bite off a nonlinear f of xu dynamics model. This is kind of the next step, right? So we're going to talk about that today. And we're specifically going to talk about a class of algorithms for the nonlinear sort of case called differential dynamic programming. Anyone heard of this before? Anyone heard of ILQR before, iterative LQR? Same thing, it turns out. Rebranding. It's basically people republishing the same stuff and making up a new name for it 30 years later. No, not to throw shade on anybody, but that's what happened. Actually, they're not the only ones. This has been republished under at least 3 different names, decades apart. The original work's from the late 60s. Maine, Jacobson and Maine, like is the original differential dynamic program, but it was republished at least one time under the name SLQ for like sequential linear quadratic something. And then again, like in the early 2000s under the name iterative LQR in the robotics community. And it's literally the same thing as like from the late 60s. So don't do this, guys. Don't do that. Do your homework. That literature survey thing in the beginning of your paper. Don't, anyway, I should shut up about this because it's going to be on YouTube. Okay, cool. So some other just kind of MPC examples that are cool that we'll talk a little bit more about later in the class. Okay, yeah, that started annoying me. Okay, cool. So cool one, like one of my favorites, being an aerospace guy, is rocket landing. Probably everyone has seen the super cool SpaceX rocket landing videos. Turns out this is done with Convex MPC. Also the Mars landing stuff that JPL does, same stuff. Super cool. This is actually a really huge result, like one of the major advances in the field, like about 10 years ago. There's a paper on this by 2 guys, Lars Blackmore, who runs the controls stuff at SpaceX now, and this other guy, Bechet Eshikmashe, who's now a professor at the University of Washington. These 2 guys, super cool. One of the like major results of the last 10 years. The basic idea is you actually model the rocket. It turns out as a point mass in this setup. The reason you get away with this is you can separate the attitude dynamics from the sort of center of mass position dynamics. this is a very common trick, by the way. This is also done in a lot of like quad rotor controllers because the attitude dynamics are relatively fast and the position dynamics are relatively slow. So you can do kind of a time scale separation of these two things. And you have like a low level attitude controller that's fast loop. And then you have a higher level position controller that's kind of sending commands to the low level attitude controller. So that's kind of the first idea. But the major thing is, so imagine you can do that. And then the main thing you then have to deal with, your dynamics now are, point mass F equals ma, super clean and linear. But the tricky part is you have a constraints on your thrust vector. And it turns out those look like a cone constraint. Like your rocket engine can, has your thrust and you can gimbal the engine and you can throttle it up and down. So the set of thrust vectors you can produce ends up basically looking like a cone. There's some details which we will talk about in a few weeks that make it interesting, but pretty much the way to think about this is I'll draw a little cartoon rocket because why not? Got our, nozzle with the smoke and fire out the back. And the idea is, you can gimbal this guy left and right, and you can throttle it up and down. If you imagine the set of thrust vectors that traces out looks like a cone. So, based on the stuff we did last time, this looks like a second order cone program is what ends up happening. So this is like the thrust limit is like the height of the cone, basically. And then the gimbal limit, like how far you can tilt the nozzle, essentially ends up being kind of the cone angle in here. It's slightly more complicated than that. We'll do it later, but it's super cool. And that turns out works super well. This is like, all the awesome SpaceX stuff kind of does this. And the JPL powered descent phase where they land on Mars does this stuff. Yeah, with linearized dynamics. So yeah, one day towards the end of the semester, I'll send you guys that paper. Thanks. And we'll kind of I'll show you the key moves, like the key tricks in it that let you do this. It's pretty cool. And of course, we'll watch super cool rocket videos because you gotta. All right, so that's a cool example. Another cool example, which we'll also talk about in some more detail, but just to kind of like throw it out there, are legged robots. Turns out, surprisingly, right? You think this is again an example of like linear models getting you surprisingly far. Like obviously a quadruped is super nonlinear. It's got all kinds of weird, crazy stuff. Turns out though, you can get again like really far with Convex MPC on these things. The standard quadruped controllers, like in particular the MIT Cheetah controller, which kind of popularized this approach, use a linearized single rigid body model for the dynamics and basically kind of abstract away the legs as like force and torque inputs, like as wrench inputs, and like set it up as a QP problem. So yeah, so imagine single rigid body, you linearize the attitude, which you can get away with it because it's basically small angles, right? You're not tilting the quadruped over too far. And the main kind of constraints that show up there, though, that you have to reason about, even under those approximations, are the contact forces that you can exert with your feet have to obey friction limits. And it turns out friction limits look like cones too. How about that? It's called the friction cone. So this is like kind of standard Coulomb friction. Let's write that down. So contact forces must obey. And we'll talk more about this later in the class. Friction cone constraint. One thing that's becoming clear, hopefully, is that cones show up surprisingly often. So your friction vector, which we'll call B, so this is the 2D friction in the, in the plane, in the contact plane. So the 2 norm of that guy has to be less than or equal to some friction coefficient mu times the normal force. And that is a standard form second order cone, like we wrote down before, right? So this guy is friction. It's 2D vector. This guy is your friction coefficient. And then this guy's your normal force. This is like the kind of fancied up, version of friction is equal to mu times the normal force that you like learned in freshman physics. This is like the legit 3D version of it. And this is a scalar. Okay, so that's what that looks like. And let's see. So if I drew the cartoon picture, you'd have your ground. This is like your foot contact point, and then you have a cone here where basically if you imagine that the total force vector, you've got your normal force N, and then your friction force B, and like the cone angle is set by that friction coefficient mu. Does anyone know what happens when I get to the boundary of the cone? The foot slips. Yeah. So if you're inside the cone, you've got sticking static friction, which is generally what you want. If you go past that, your foot starts to slip. So that's what that friction cone means. And then what people often do is approximate the cone with a pyramid. Why might I do that? You don't have any ideas?
They're not able to, are they fully degrees of freedom, like legs that can move? Or
yeah,
in two directions.
The reason I do it is so that they can rewrite it as linear constraints. So you basically replace the round cone with a bunch of flat sides to make a pyramid, and now it's a QP. So that's why. So they can use QP solvers. It's still convex like this. It's a second order cone, but the popular thing is to linearize, like make it a pyramid, and so you can solve it as a QP because QPs are fast and stuff. Yeah.
So is it the largest square inside the circle?
Yeah.
Or the smallest circle probably?
No, it's generally people using a conservative inner approximation. Like if the idea here is you don't want the feet to slip, you want to use an inner approximation, right? That's conservative. So that's what people do. So yeah, so the constraint is linear. So then you can write it as AX less than equal to B. And now you've got a standard QP. You don't really need to do this. I think this is kind of a historical thing where 10 years ago, there weren't very good fast SOCP solvers, and QP solvers were kind of better. So people did this back then. But yeah, so what this would look like is you kind of do this kind of thing, right? So you have your four sides of your pyramid. I don't know, that's not a great drawing, sorry. And so this whole scheme was originally kind of popularized by Song-Bae Kim's group at MIT on the cheetah robot. And there's a bunch of papers on this stuff where they, there's a series of them where they develop this kind of stuff.
Is friction not dependent on the size of the foot?
Turns out not really, no. This is the Coulomb friction. So it is in real life, but the Coulomb model, the Coulomb friction model, turns out it's independent of the surface area. This is like a, kind of first order approximation of the real friction. Real friction is way nastier and more complicated, right? So you get the first thing that shows up in real life is you get a difference between static friction and sliding friction, which isn't captured here. What that would be is mu would change at the boundary of the cone, which doesn't happen here, right? And then there's even weirder stuff that happens as you start sliding. There's this thing called the Strybeck effect. So it turns out your friction drops as soon as you break static friction, but then it creeps back up again as velocity increases, all kinds of weird stuff. It's very, very messy in real life. So this is kind of a very first order approximation of real friction. Yeah.
So the cone are driven by what is actually, it's how much you're pressing kind of into the ground.
Yeah. So the harder you press down, the more you can press sideways. So that's what this captures. And the cone is really just capturing the boundary of slipping. So really this model is good if you're just trying to prevent slipping. If you're actually trying to reason about the dynamics while you're sliding, it's not very good because weirder nonlinear things happen when you're sliding. So usually, but this is perfectly valid if you just care about not slipping your feet, which is the standard thing. Yeah. Cool. All right. So MIT Cheetah does this. And basically, this is the standard MPC setup on a quadruped. This is what everybody does. So they do this trick, and then they use linearized rigid body dynamics, like small angle approximations like we did last time on the quad rotor. And it works really well. Okay, so those are just a couple examples. We'll dig into these more, but I just want to give you a taste. Like this stuff is again like surprisingly useful, right? You look at this stuff and you're like linear models, meh, whatever. Like it doesn't, everything's nonlinear. But if you're a little clever about how you set up your model and what things you linearize and stuff, you can take it really, really far. And it's super useful and powerful. Okay, so that's going to lead us into our next topic. What about nonlinear dynamics? Ugh. Okay, so basically linear stuff often works well. So I would suggest you do the linear stuff first if you can get away with it. Because it's super well understood. The algorithms are rock solid. It always works. You can always solve those convex problems, right? There's good hard real-time stuff. So if you can do it, it's probably a good starting point. But there's obviously situations where it's going to break. But it should be your starting point for a lot of stuff. Okay, so yeah, reason why, like if I take even if I have like relatively benign, quadratic cost, blah, 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 as soon as I put nonlinear dynamics in there, it makes the MPC problem non-convex, right? So, let's see. And that basically means that like all of our nice convergence guarantees about like with Newton's method kind of go out the window. And you can't really say anything. You can't, not only can you not say anything about like getting a global optimum, you can't even say anything about like, how many iterations it might take to converge, like all this kind of stuff, which makes online implementation kind of scary, right? Like if I don't know how many iterations it might take, it might take 2 sometimes, it might take 20 sometimes, it might never converge sometimes. It's a very scary situation to be in like a hard real-time environment where you have to like run the thing on the robot or it might face plant or you might crash your rocket or whatever, right? So yeah, that's why we tend to not do this if we can help it. But that said, lots of people do this and it works really well in practice if you can like hand engineer some stuff, do a bunch of tuning, Monte Carlo it a lot. Like you can get this to work really well. In fact, extremely well. Like this is kind of nonlinear MPC is basically what like Boston Dynamics does on Atlas. So all that insane stuff that you see them do, that's nonlinear MPC, where they're basically doing this stuff online. They're kind of the best people in the world at it, and they've really dialed that stuff in, and they've done amazing like stuff there with like years of effort. So you can get it to work, right? But it's sort of the Wild West, and it takes a lot more tuning and kind of effort to make it work than the convex stuff. But another area where this is really big, it turns out, is autonomous driving, somewhat terrifyingly. Like all the cars are basically doing nonlinear MPC with like nonlinear bicycle models to drive the cars. So, same story, obviously works. You can make it work pretty well. I'd say that's maybe the less sketchy part of the autonomous driving stack. Like the perception part of that is the part that's really scary. But yeah, so it works, right? People do it. It's a real thing. You shouldn't be scared away from doing it at all. It's like do it if you need to kind of thing. But if you can get away with the convex stuff, it's a much nicer place to be, right? Okay, any questions about this? Cool. All right, so now we're gonna do that. We're gonna do the nonlinear stuff and talk about like how you might go about that. Okay, so first off, let's just write down, we'll revisit our kind of general optimal control setup and write down kind of the nonlinear problem. So this is the nonlinear trajectory optimization problem. And it's basically what we wrote down before for the general case here in discrete time again. So we've got our X and U trajectories. We've got our cost function that's just added up over a bunch of time steps. So 1 to n minus 1, got your one-step cost, which could be time varying. So I'll put a little subscript on it. And then we've got our terminal cost that just depends on the final state. In general, this can be non-convex, right? These L's can be anything you want. Can be non-convex. Then we've got our our dynamics constraints. So those look something like this. And right, these can be nonlinear in general. That's the part that really matters, right? The cost function, we can generally get by with quadratic costs and stuff, but and then you might have other constraints, right? So like obstacles and stuff. We're going to write these in like a more abstract notation like this. Say X has to be in some set big X. So this would be like your obstacles or whatever, right? And then same deal with U's. The U's have to be in some set big U. So that'd be like torque limits or whatever. The difference here, right, in general, these can be non-convex now. That actually shows up all the time. Like obstacle constraints are usually non-convex, right? If I'm saying like, this podium, you're not allowed to hit this podium. The free space that I am allowed to be in, like the podium might be convex, right? It might be a big block, but like the free space that I'm allowed to be in is non-convex, right? It's like something with a big hole in it. So that happens all the time. Okay, so these are non-convex also. Okay, so that's the general situation. So this is what we're going to try to attack now. The one note I'll say is we usually assume that everything in here is at least C2 smooth. That means it's got at least two nicely behaved derivatives. Like you can take the first two derivatives and nothing weird happens, right? So just that they have continuous first and second derivatives. That gets violated quite often in robotics, it turns out, in particular contact problems. Like when I do that, things are non-smooth. So this is not universally true. In fact, there are many, many things we care about where this is not true, and we'll talk more about that later. But for now, we're going to assume that things are smooth. And the reason we're assuming C2 smooth is this should be obvious, right? We're doing Newton's method. So we got to take gradients and Hessians to do Newton, right? That's basically it. This is what you need to do, like, basically do Newton. Okay. Any questions so far? That's what we're doing. Okay, so now we're going to talk about differential dynamic programming. This is like one of the workhorse algorithms. There's basically like two major workhorse algorithms for this like nonlinear trajectory optimization stuff that are used in robotics. DDP is one of the big ones that's super popular and super common. Interestingly, people generally seem to fall into one of the two camps. Like labs tend to do one or the other and have like they stake out their turf. Okay, so this is DDP. So the idea here is this is a nonlinear trajectory method. That, as the name might suggest, is based on approximate dynamic programming. So it's taking that dynamic programming story that we did, and it's doing some stuff to approximate the value functions so that it's tractable, right? Cool. And the key idea here, like you can kind of guess what that approximation is going to be by the theme so far is basically what we're going to do is Taylor expand the value function and just kind of iterate that. So we're going to use a second order Taylor expansion. Of the cost to go in dB. And use those to compute Newton steps, basically. So you can think of this as like a mashup of dynamic programming and Newton's method. And the key idea is you like do a second order Taylor approximation of the value function, and you use that, you then minimize that thing, right? And you just repeat that.
You have to do that about equilibrium, or is that work the whole trajectory?
Yeah, so the idea here is we're doing this like without knowing anything, right? So this is like trying to find the full trajectory without necessarily a super good guess. So this is like kind of a way to do Newton's method in the dynamic programming context for like the whole trajectory. Yeah. And yeah, so these are this is a very popular class of algorithms in robotics. There's pros and cons. We'll talk more about that when we do the other kind, which are so-called direct methods or collocation methods. Generally, the reason people like these is number one, they can be very fast if done well. And number two, they are what we call anytime dynamically feasible. That means that the iterates that you get out of this are always obey the dynamics. So that means you can basically stop early before it's fully converged and still run it on the robot and expect reasonable things to happen, which is not true of the other kind of the direct or collocation methods. Those don't necessarily obey the constraints until they've fully converged. So these for that reason, they tend to be popular for like real-time MPC kind of things where you want to stop early. Okay, cool. So let's do it. So the first sort of idea here is this idea of just like Taylor expanding the cost to go. There's like a general, I think one of the main like, kind of dividing lines between optimal control and RL is what kind of function approximations you like. Optimal control, Taylor expansions, polynomials. Throw a neural network in there, now it's RL. I don't know, whatever you like. But yeah, this is kind of the old school stuff. Literally though, like if you were to use a neural network to approximate this instead, then you'd be doing deep RL. So, it's all the same stuff. It's kind of, I think, the meta point. So we'll do this cost to go function thing. Cost to go expansion. Okay, so we got our V from last time. And what we're going to do is expand this about some X, and we're going to write the expansion in terms of some delta X, right? So this is going to look like V of X plus little p transpose delta X. So that's like the gradient term. And then a Hessian term that looks like delta X transpose big P delta X. So that's really the same thing we saw last time when we did LQR, right, with that big P, with one difference, which is that now we have a little p gradient term in there as well, right? With LQR, we only have the Hessian term. Now we've got the extra gradient term, right? So basically, this is gradient and Hessian. And we're going to start this thing out just like we did with LQR. We're going to start at time n. And at time n, we're just looking for, Vn, which we're really looking for Pn, little p, big P at time n. And just like with LQR, that's just coming from the terminal cost. And in this setting where we've got like a general non-convex whatever cost, what we're going to do is just Taylor expand it to second order to get these p's. So we got little pn is just going to be the gradient of our terminal cost. And then the big one, the big P, the Hessian one, is just going to be the Hessian of our terminal cost. And I'm going to use like sub xx to mean like the Hessian with respect to x. So that's d squared x, d squared L d x squared, right? Okay, so that's how we bootstrap at the last time step. This is all going to look very much like the Riccati stuff from LQR, just with some extra terms, namely the gradient terms. The Hessian parts of this look pretty much the same as what we did before. Okay, so that's that like terminal, cost term. What we're going to do now is like do the same kind of Bellman backup thing as we did before with the Riccati stuff. We're going to write it, though, this time in terms of the action value Q function thing. I'm not going to call it Q, though, because obviously cost overloading with LQR, but we're going to write it, we're going to call it S, and I'm going to write this out in terms of S. It just makes the derivation a little cleaner. It's just easier to write it that way. So let's write that down. So we're going to expand that thing to second order. Same deal. So we've got S at time k, and this is a function of the state So we're going to Taylor expand it in some delta x and then also the controls. And so if I Taylor expand this to second order, I'm going to get the constant term at x and u. Then I'm going to get a gradient term. And I'm going to use little g and big G for like the gradient and Hessians of this guy. So we've got a gradient term, and I'm going to separate out like the x and u components of this guy. So that looks like that, times delta x, delta u. And then the Hessian term, no surprises, right? It's going to be delta x, delta u, transpose. I got this Hessian thing, and I'm going to write it out blockwise and kind of write the x and u parts. So I've got gxx for the x part, the cross term, which is like partial respect to x, partial respect to u, like mixed partial, we're going to write as gxu, and then gux, and then guu. So we just got the block written out blockwise, times delta x, delta u. And this, remember this Hessian, this thing's symmetric, right? So we've got for this guy that gux equals gxu transpose. So I only need to kind of keep track of one of those guys. Okay, so that's just like very, very simple second order Taylor expansion. So we're going to assume like you've got that. And then we're going to write down the Bellman backup, the one step thing. Again, very, very much like just like what we did last time with LQR, just got a couple extra terms. So we've got Vn minus 1 of x, or k minus 1 or whatever, doesn't really matter, is let's write k, is min over delta u of this whole thing. So I'm going to write the whole thing out. So we've got s k minus 1 of x u, which is a constant, so that doesn't affect anything. Then I've got the gradient term. So I've got gx transpose delta x, gu transpose delta u. And then I've got all these Hessian terms. So I'm going to write those out individually. So we've got delta x transpose gxx delta x. We've got the u term. So that's 1/2 delta u transpose guu delta u. Then I've got those mixed partials. So that's delta x transpose gxu delta u and 1/2 delta u transpose gux delta x. And those last two are the same because it's symmetric. So that's just me expanding that thing out. And then what do? This looks pretty much exactly like what we did before with Riccati. I'm just going to take the gradient with respect to delta u and set it equal to 0. So to save myself some writing, I'm just going to write out like grad with respect to delta u of this thing. And this is really simple now. This is just gu. And then I got the quadratic term gives me guu times delta u. And then the mixed terms give me gux delta x. So those, remember those bottom two are the same, right? They're just transposes of each other. So that's all good. And so we set that gradient with respect to u equal to 0. And now I can solve for delta u in terms of everything else. So I got delta u n minus 1 or k minus 1, kind of assuming this kind of recursion, thing, k minus 1 is minus guu inverse times gu minus guu inverse times gux delta x. Okay, so now what we're going to do is give these things names just like we've done in the past. So this term, so this is our delta u, this term doesn't depend on delta x. This is a constant as far as we're concerned. It's just like a constant update. So this guy, we're going to call this little d. So this is going to be dk minus 1. And then this thing is a feedback term, just like LQR. It's some matrix times delta x. So we're going to call this guy k, just like we had before. So this is k minus 1. So now this whole thing is minus dk minus 1 minus big K times delta x. And we're going to kind of think about this as this is like a feed forward term or a feed forward correction. And then this is a feedback term. And really this term, the second term, is just the LQR. It's the same thing you would have gotten with the LQR controller. And this extra term is coming from the gradient stuff that's new. And that's the only part that's like different from LQR. Okay, so we're put a box around this. Not so bad. There's a lot of kind of like math gymnastics to get to the end of this one. Okay, so that's pretty good. So the next step is, like we did before, we've got delta U. Now we got to get the cost to go at the next time step. So we got to plug delta U back in to our expression up here to actually get the VK minus 1. So we'll do that real quick. Hopefully quick. To S K minus 1 to get VK minus 1 of X plus delta X. That's what we're after, right? So if I go and do that, got V minus 1 of X plus, this is just me writing down like the terms I'm looking for and the form of this thing. So that's the gradient term, and then the U term is going to be minus D minus K delta X. I just plug in my new delta U. Then I'm going to just keep doing that, right? Just plugging in all the stuff. So I've got delta X. I didn't do anything to that. That's still in there, but I'm going to plug in the delta U's everywhere. So I've got the D, K, delta X times GUU, same stuff. Subscripts get really annoying to write. And then, yeah, those mixed terms, blah, blah, blah. And that last term. Oh, I did that backwards. Okay, so that's that plug back in. And now I can like kind of collect some stuff and simplify that down. And what I'm really after here is I need little p and big P. So this is just like we did with Riccati, where I plug it back in, I squish stuff around, and now I've got it back into the sort of form I wanted. So I've got Pn minus 1, or K minus 1, rather. Can't tell the difference anyway with my handwriting. So GXX plus K minus 1 transpose G U K minus 1. And then you've got like these kind of mixed terms. So that line is the exact same thing we got with the LQR Riccati stuff. It's just kind of written in slightly different notation. So you can go check that out if you want. And then the little p, which is new, which we didn't have before, looks like the following. Okay. So that's that. Put a box around that. These are like the key things to implement the algorithm. So this is your backward recursion. It's like a, Riccati plus. This is the feedback law you're going to solve for, right? So now we're basically there. We bootstrap the algorithm. I can calculate this D and K, I can plug it back in and get the new P's, and then I can go back again, right? And keep moving back. So this is like we have bootstrapped. There's like one extra little nugget that we kind of glossed over here, which is I didn't really tell you how to compute the G's. Right. So they're like Taylor expansions of stuff we know. They're Taylor expansions of like value function things and dynamics things. Yeah.
It's just derivative thing previously.
Sorry.
About the derivative term.
Yeah, sure.
So when we're taking the derivative with respect to delta U, why like the last two transpose terms can be combined to one d x delta x?
They're the same thing. So these two guys here. Okay, so first off, these are like the cross blocks in the Hessian.
Yeah.
Hessian's got to be symmetric, right?
Mhm.
So those are transposes of each other. And these two, so this equals this transpose, right?
Yeah.
Okay, so we agree on that. Like these two are transposes of each other, and they're scalars. You see that? This is a scalar, the whole thing together. Right? It's a quadratic form.
Yeah,
Okay, so what's the transpose of a scalar?
itself.
It's up. So these are equal. Does that make sense?
Yeah.
Everyone cool with that? Okay. Okay, so this is a okay, deep breath. Cool. That was kind of a lot of math and whatever. The basic idea though is it looks very much like your backward Riccati situation. It's just got this extra set of terms now. So we compute this like these G's. We've got like, given the G's at a given time step, I compute this delta U update, plug it back in, and I get my new P's. So that's like getting me from action value to update on U to new value function. But now what I got to do is compute the new action value Taylor expansion, which we didn't quite do yet. Yeah.
Is your Costigo function still k minus 1? Shouldn't it be k?
I'm going backwards. So I go from k to k minus 1 to k minus 2. Yeah. Yep.
I'm missing 1 over 2 for to the last one.
So this guy, yeah, I think you're right. Yes, thanks. Good catch. Okay, did I screw anything else up? Probably. I try not to, but it happens. Okay, cool. So, all right, so here's where we're gonna do a little weird detour. So now what we need are, we need to compute the little g and the big G. These are Taylor expansions of that action value function thing, right? We could leave it at that, but I don't know. This always bothered me, so I'm going to teach you how to actually do it for real, which means we need some more math. Just a general interest. You could totally zone out for the next 10 minutes if you want to. This is not like super important for like the class, but it's a general interest topic that like, I don't know. It shows up here. Most people who do this in papers and stuff will just completely like gloss over this and say, oh yeah, whatever, tensors, blah. I'm gonna show you how to do it for real. So we need some math. What basically happens here is we have to take second order Taylor expansions of the dynamics, which this is a function from Rn to Rn or whatever. So it's, the first derivative is a Jacobian matrix. What's the second derivative of the dynamics? Okay, so this whole thing, we're going to call this matrix calculus. And the situation is, given some f of x, i.e. think about the dynamics from Rn to Rm or whatever. So it's each a vector spits out another vector. We're going to look at the second order Taylor expansion of this guy. Okay, so if m equals 1, so i.e. it's like a cost function where it spits out a scalar, then we know what we're doing. So if that's the case, we've got, f of x plus delta x is approximately f of x plus a gradient term, partial f, partial x, where that gradient, and then a Hessian term. So you'll have like what we've been doing, right? Delta x transpose e squared f, ex squared delta x. where we know these guys are. So this guy is a row vector, gradient. So this is 1 by n. And then this guy's our Hessian matrix. So this is n by n. So we all know how to do that. That's how we like get our second order Taylor expansion of our cost function. But what if we're talking about like a dynamics thing where it also spits out a vector? So let's write that out. So if, say, m is greater than 1, so we've got some kind of deal. We've got our f of x. Then we've got our first derivative term, df dx. And for us, if this is a dynamics function, this is that A matrix, right? So this is already a matrix. This is like m by n. And now the second term in this Taylor expansion is going to be something like, I'll write it out in a way that's correct, but sort of unwieldy. It's like if I have my df dx times delta x, and then I took another derivative of that and then multiplied by another delta x. So this is a way I can write it that's legal, but basically, if I wanted to pull this in here, I get like this second derivative of f thing that is what we call a third rank tensor, because it's got to eat 2 vectors in and spit out another vector. All right, so this is ugly and messy, and we don't want to do this. And we need essentially a way to, who knows what a tensor is? People have heard of this before? Most people. Okay, so the idea here is like, if I have something that needs to eat 1 vector and spit out another vector, that's like a nice matrix. You know how to deal with that. If I have something that needs to eat 2 vectors and spit out a scalar, that's the Hessian we know, where we're going to multiply on both sides by delta x's. If I need something that eats 2 vectors and spits out another vector, this gets weird. So you could imagine writing that down component-wise, where I'd have a bunch of Hessian matrix sort of looking things that would spit out each component of that output vector. And if I wanted to somehow, you could imagine taking that and like, stacking it this way and getting like a 3D matrix, right? It's like a matrix that has 3 indices. That's what that's called a third rank tensor. It has 3 indices, right? So it's all about how many vectors it eats to like spit out a scalar, basically, is what that rank is. Okay, so that's kind of what we need to do. And I'm going to show you like a set of tricks to let you compute these things in a legit way and do kind of all the tensor math you'll probably ever need without actually having to write tensors, just with like basic matrix math. So yeah, the story is for m greater than 1, this d squared f dx squared thing is a third rank tensor. You can kind of think of this as like a 3D matrix. And basically, I'm going to show you some tricks for dealing with this in a like standard matrix vector kind of setting. Okay, so there's basically 2 tricks. And if you know these 2 tricks, you can do pretty much all of tensor calculus without leaving the comfort of like MATLAB or NumPy or Julia, which is great. So the first trick is something called a Kronecker product, which you've already kind of seen me hint at, that cron thing where I use that to build these sparse matrices. Super fun, super useful. It's a good little nugget to take away from this class, I guess. Teach you weird linear algebra tricks. So here's what this thing is. You write it like this. So it's this, times in a circle thing. It's called O times in LaTeX. And if you say it out loud, we usually say that as A cron B. And you write it as KRON cron in MATLAB, Julia, Python, whatever. So the idea is it's a product defined on 2 matrices. And let's say this guy is L by N, and this guy is N by P. What this is going to do is take the matrix on the right. So it's going to take B, and it's going to make a really giant matrix as the output that is each element of A, each scalar element of A times the entire matrix B. So imagine taking every single scalar in A and expanding it by multiplying it by the whole B matrix. So I'll write this out, kind of what this looks like. So it'd be like A11 times B A12 times B dot dot dot, like A21 times B, A22 times B, and you just kind of, you get the idea, right? So you get a really huge matrix that ends up being dimension Ln by MP. This is an N. So it's basically, you know, the products of the dimensions of the input matrices, right? Everyone cool with that? So it's just a definition. It's a thing. It turns out it's kind of useful. So I used this, remember, to build these big sparse matrices by like making A the identity and then B, you know, like whatever I want. And that gives me a nice block diagonal matrix. So if I want to make a block diagonal matrix out of like A, I can do I cron A, and then I'll just get A down the block diagonal, right? So it's really convenient for building like weird, big sparse matrices. Fun fact. Okay, so that's the idea number one. Idea number two is this thing called the vectorization operator, or vec for short. And so if I have a matrix A, what I'm going to do is think about the columns of A. So I'm going to define like A to be like A1, A2, A3, dot, 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 to like AM. Yeah.
Could a big matrix not be LM times NP?
Ln, let me think about this.
I mean, it's the L rows of A.
Yes. Yeah, you're right. Thank you. Cool. I think I messed. Oh, yeah. So the bug was here. I meant for these to be L by M and N by P, so that this is Ln by MP to be consistent with the next line. Like that's right. Okay, so this is L by M again, and then these are just the column vectors of this guy. And so we define this vec operator. So vec of A, it just takes all the columns of that A matrix and stacks them in a big vector. And this guy then is Lm by 1. Cool?
Or shaping into right?
Hmm?
It's like it's the same as reshaping into -1, 1. Right?
Yeah, so in MATLAB, this is actually just like A colon or Julia, which is cool. So yeah, there's ways to write this in different languages, different ways with index tricks. But yeah, we're going to define it as this vec operator, vec function. It's actually called vec in some languages too. In MATLAB, it is called vec. I don't know what it is in NumPy. But yeah, you can get this by doing weird index things too. You can do it in any of one of these array kind of languages in different ways. I'm not a big Python guy, so I don't know the NumPy stuff as well. But yeah, cool. Just stack the columns, right? And you get a vector. Okay, so here's these two things, the definitions. And then the last little nugget is that makes it all work for all the weird cases we care about is called the vec trick. I don't know if there's probably some other name for this. I just know it as the vec trick. And that's what I call it. I don't know if it has a more official fancy math name. The vec trick is the following thing. And if you stare at this, you can kind of figure it out. It's vec of A, B, C, where these are matrices, equals C transpose cron A times vec of B. It's cute. And it turns out there's a special cases that we use all the time where we kind of make one of these the identity. So this means like vec of A times B is equal to B transpose cron I times vec A. It's also equal to I cron A times vec of B. So the reason we care about this, where we're going with this is how you differentiate like matrix expressions with respect to one of the matrices. That's like where we're going with this, which is what we need. Okay, so and then there's like one last, I don't know, little thing that I'll tell you about because it might show up. It does show up in this case. Basically, so this is all good. This lets us like diff, some bunch of matrices multiplied together. Like it lets me diff it with respect to B, right? So like the rule is if I want to take the derivative with respect to something in there, I move the thing I want to differentiate with respect to all the way to the right. And then whatever's left in front of it is the Jacobian, right? So that's kind of how I use that. And last little thing is if we want to diff, okay. Yeah, okay, there's a couple little, okay. So if we want to diff a matrix with respect to a vector, which is the case when we're trying to get that dynamics second derivative, right? I can imagine, I've got df dx is like my A matrix of my dynamics. The next derivative is dA dx, right? So it's like derivative of that A matrix with respect to x is that second derivative. So that's the situation we're interested in. What we basically just do is we vectorize the matrix. And then it just looks like a standard Jacobian that we know how to deal with again. So anytime you see something like this, where that's our dynamics A matrix, say, we're going to basically always assume we're doing this. So that like vec is always kind of implied anytime you see a matrix derivative like this. Turns out that works great, and you can like still do the chain rule and all that good stuff too. Let me just write in the dimension of this guy. So this thing is Lm by n. So x is n dimensional. Cool. Okay, so now we're going to go back to our Taylor expansion of our f of our dynamics A. Okay, so we got f of x plus delta x, approximately f of x plus df dx times delta x. We call this guy A, like assuming this is our dynamics, right? We've got, I'll take a little detour here. What we're going to do here is take b dx of, we're going to vectorize the whole thing, but the way you get this is by looking at it like I times A of x times delta x. Make sense? So I'm using the vec trick where I've got vec of ABC and I can pull the thing in the middle out. So I know vec of I times A times delta x equals, well, I'll write it here now, but it's that vec trick from before. Just, it looks a little weird. I'm trying to just explain the trick. So I've got, if I do the vec trick on that expression down there, I get delta x transpose cron I times vec of A. And then I diff vec of A, and I get b squared f dx squared, which is just dA dx, right? Times delta x. So, which is, this is, and then this guy is partial vec of A partial x. Hopefully that all made sense. Everyone cool with that? It's a little bit of, this is just like gymnastics and definitions, but this lets us take those second derivatives that we want for the dynamics to get the second order Taylor expansion of the action value function, blah, blah, blah. Okay. It's a lot of, I don't know, this is kind of interesting. You're not gonna find this too many places. So I don't know. I got obsessed with this for a while and then eventually figured this stuff out and stumbled upon it. So now I'm giving it to you, it's free. Okay, so last thing, sometimes we also need to worry about transposes when we're doing this. So we need to diff through a transpose. So if I've got, for example, b dx of A transpose B, what I'm going to do is write that like this. So I've got B transpose cron I But what I'm going to get now is A transpose. I want the derivative with respect to A. So I'm going to make up this new matrix. We'll call it T. And that basically, I'll define it. And it's, yeah, let me just write this and then I'll tell you what it is. So we define this thing such that P times vec of A equals vec of A transpose. So it's literally just a permutation matrix. It's just swapping rows and columns around. So I can make that work out. And this thing has a name. It's called the commutator matrix. Okay, that's everything. That is all the math you need. In fact, this is all the math you need to pretty much do all of tensor calculus, I think. So now you don't have to take a class on tensor calculus. Now you just do this stuff, and you can still use MATLAB and NumPy and stuff, and life is good. All that Einstein index notation crap, you don't need it. You just do this. It's great. Also, this plays nice with like sparse matrix toolboxes and stuff, which is great. There is a NumPy library called EinSum that lets you do the Einstein index version of this. But I don't know, this is easier for me. So that's what I do. Okay. Now we're gonna make yeah, sorry, Jim.
Get G and big G.
That's what we're gonna do right now. Yeah, sorry. That was a little interlude on like tensor calculus and stuff. And now I'm just gonna tell you what those expansions are. Okay, so action value function derivatives. This is the last piece of the whole thing that we needed. And then I'm going to tell you a punchline at the end that might make you regret this whole thing, but here you go. So this is our at time n, yeah. Or sorry, k, time k, trying to like parse my own handwriting now. This is bad. We've got LK, our one-step cost. This is the action value function in terms of the, it's the thing inside the min in the Bellman thing, right? Remember from last time? So we got our one-step cost, and then we've got our value function at time k plus 1 with the dynamics plugged in. So I want to take the second order Taylor expansion of this thing, right? That's what our action value function is. So I'm literally just going to go chain rule this thing and write out all the derivatives. The first two are easy. So let's do those. So we got partial S. These we know how to do, and we didn't need that whole math interlude for this. Partial L. Sorry. Okay, so this is partial of our one-step cost. Plus, we're just going to chain rule through the next part, right? So we got partial V, partial, I guess I'll write it as partial V, partial F. It's just derivative of V times partial F, partial X. All right, so I'm just chain ruling that second term. Cool. And this guy we call A, remember, right? That's our A matrix from our dynamics. And then the next term is the same deal. It's just the U derivatives. So this is partial S, partial U, and it's just DL, DU, and then same kind of deal over here. We'll say DV, DF times DF, DU. And remember that we know is B. It's our B matrix from our dynamics. Okay, so these two things, we're just going to now like use our definitions. So this is little g sub x from before. It's that gradient block. So this is, if I wrote it in our other gradient notation, this is grad sub x of L plus A transpose at time k times little p k plus 1. Right. Remember, df dx is little, yeah. dv df is little p. And then same deal over here. This is g sub u. And then this is b transpose little p. So yeah, right. Dynamics are A and B. And then this grad of our value function is little p. Hessian of our value function is big P. That was like where we were at the very beginning. Hopefully this isn't too much jumping around. Okay, so we're going to put boxes on these. These are all the important bits that you need to actually implement this. And then the annoying part, which is all that tensor crap that we just did. Okay, so here we go. I'll just write it down, and then like we can talk through it a little bit. So all the things you need, gxx, this is that Hessian with respect to x. And the way we get it is literally just, we have little g, this is just the next derivative of little g, right? So it's partial g sub x with respect to x again. Okay, so if I just kind of stare at that and like do the chain rule, I've got Hessian with respect to x of the one-step cost. It's that first one. Then I'm gonna diff the second term, and this is where it gets kind of weird. So if I take first, if I diff it with respect to little p, I get the following. I get a transpose del squared v. I should write this as big P. A. So that's the P derivative. I should write that. I just write that as big P. That's big P. Okay, so that one's reasonable. And then this is the annoying one. This is the whole reason for all that interlude. I get, if I diff it with respect to, I diff through the A, if I chain rule through the A, that's where I get this like tensor stuff. So I'm going to play the Cronvec trick. I've got P cron I transpose. Then because it's A transpose, and I need to diff through the transpose, I get that commutator matrix guy. And then it's dA dx. Okay, so that's the whole thing. It's just doing a chain rule. I'm going to write down the other two. So this is the derivative of like the u gradient with respect to u again. So this is d squared u of our L. And then this is B transpose P B. And this is very similar looking tensory thing. And then the last one is that cross term, the mixed partial. So this is, you can get this both ways. We're going to write it like partial of that G sub X respect to U. You could also do G sub U respect to X. You could do it either way, right? Because it's symmetric. It's got to be the same both ways. So this is the mixed partial of the one-step cost. And then it's got this kind of cross-term flavor here. And then it's got a similar looking tensor thingy over here. And this you can write kind of either way because of the symmetry. So it could be partial A, partial U, or partial B, partial X. Okay, that's the whole thing. It's a little nasty. Let's move this down a little bit so I can put a box around it and then say some stuff. Okay. So the first part of this is basically the standard Riccati equation that we got before for LQR in this part, right? So the first couple pieces of that. So this is new. We didn't have this last time, but the first couple chunks of this are just the Riccati equation stuff from last time. The new part is this last part. So I'll put a box around this separately and say, we're going to call these the so-called tensor terms. Okay, punchline is, so that's differential dynamic programming. You have all the pieces now. We're going to do it in a sec. I'll just make one extra little note. So we mentioned at the beginning, some of you guys have heard of ILQR or iterative LQR. It sounds like more people have heard of that than DDP before, which is funny because DDP's from like late 60s and ILQR is from like 2004 or something, and they're the same algorithm. Okay, there's one difference between those two algorithms. Difference is, so this is differential dynamic programming. If you leave out these tensor terms, if you just throw them out, which it turns out, which is basically, remember how we talked about full Newton versus Gauss Newton? Those tensor terms are the full Newton version. If I throw them out, it's the Gauss Newton version. Basically, that's what's going on here. the tensor terms are they're the Hessians, the curvature terms of the dynamics constraints. That's what's going on here, right? So if I throw them out, I get a Gauss-Newton version of DDP. Turns out Gauss-Newton DDP is what ILQR is. ILQR is the Gauss-Newton version without those terms. If you use those terms, if you throw them in there, it's DDP. If you throw them out, it's what I would call Gauss-Newton. That's what people usually mean by ILQR. Although I would say more often than not, people just throw those out all the time because they're a pain and still call it DDP or ILQR or whatever. So for all intents and purposes, people do whatever and call it whatever. But I think if you go back to the papers, those terms are in the DDP paper. They're not in the ILQR paper. But people basically use all those things interchangeably. And I'd say the majority of implementations out there throw those tensor terms out because they're a pain to compute. And like same story when we talked about Gauss-Newton versus full Newton, like those terms are expensive to compute and they tend to not help all that much. So in terms of wall clock time, it usually isn't really worth it. And you just throw them out and do the Gauss-Newton version. Okay, so now we got code. So we'll do this.
So is it?
Yeah.
If you're throwing out the tensor terms, aren't you kind of just doing the first order Taylor extension?
You're doing a first order Taylor extension in the dynamics, but still second order in the cost function. And right, so it's that sort of half thing is called Gauss-Newton. So Newton is you second order Taylor expand everything. Gauss-Newton, you second order expand the cost function, like the objective function, but only first order Taylor expand the constraint functions, right? That's basically what it is. So Gauss-Newton's sort of like a halfway, kind of thing where it's throwing out some of the second order derivatives. But turns out it works really well in practice and people do it all the time. And so that's kind of the official difference between ILQR and DDP. But I'd say in a lot of cases, people don't bother. Okay, so before we leave, let's do this on something fun. Has anyone heard of an acrobat? Has anyone heard of a double pendulum? Okay, acrobat is a double pendulum with a motor at the elbow joint. So it's got a passive shoulder. It only has one motor. So it's 2 degrees of freedom, only one motor. The reason it's called an acrobat is it's like kind of used as an approximation of an acrobat swinging on a trapeze, where you can bend your waist to swing, but you can't really exert torque with your wrists. So it's an approximate like acrobat kind of vibe. That's why it's called the acrobat. These are the dynamics. I'm not going to ask you to know anything about this or write them down. This is just, that is what it is. It's kind of gross and nonlinear. It looks gross, right? Okay, we're going to take that, use RK4 on it like we've done many times. We're going to write some Jacobians down, and I'm going to use for diff and be lazy and not actually write them by hand, as you should do, because, computers. Okay, so this is just some random, time step, like 20 hertz, bookkeeping, 10-second trajectory, blah, blah, blah. Cost function stuff, we're going to use like a simple quadratic cost like we've been doing. Those are some cost weights. And this is just calculating some cost stuff. So stage cost, terminal cost, the full cost added up. This ends up being important, it turns out. So this is an initial guess at our trajectory, and this will come up. So what we're going to try to do here is take the acrobat, start it down here, and have it swing up here and balance. That's like, it's cool. It's kind of fun. So the X naught is just hanging down like this, and the X goal is up here like this. That's what that says. And then we have to make an initial guess for this algorithm. It's a Newton type of thing. We're going to make an initial guess. Turns out with this stuff, what you end up having to do is guess an initial control trajectory. You don't get to guess the controls and states separately because part of the algorithm is doing a rollout. So I'm going to simulate it forward with this U trajectory and get what I get. That's what's going on here. So I'm going to just initialize with random noise, which is a pretty standard thing to do. And then roll it out. And then here's the algorithm. So I'll do a quick, because we're out of time, I'll just show you real quick and then we'll talk through the details. Basically, the way this works, this is wrapped in an Armijo kind of thing. And this is a convergence tolerance. It says if the Ds, the feed forward corrections, get less than 1e minus 3, I'm done if I'm not moving. And so I do a backwards pass where I calculate all the stuff we just talked about. And then so I get my D's, K's, P's, I go backwards. Then I do a forward rollout with a line search. So when I do the forward rollout, I'm taking the feed forward and the feedback corrections, and I'm sticking an alpha on there. and doing my usual backtracking Armijo stuff. And I'm doing a rollout each time in my backtrack. So I apply the correction, roll it out, evaluate the cost. If the cost satisfies the Armijo thing, cool. If it didn't, I chop alpha in half and try again, right? Same sort of thing. And I do that until I hit, this is the Armijo right here. I do that till I hit my convergence tolerance. Let's just run it since we're kind of out of time, and I'll show you what happens. Yeah, so this is just showing you like the progress as it goes, which is a good idea. So we did about 300 iterations. Here's what comes out. And yeah, that's states controls, but more fun is to animate it. So let's do that. Pretty sick. Okay, yeah, out of time. We'll do more next time. I'll show you but yeah, we'll play around with this a little more. Also, the code will be online so you can try it. Fun things to try if you go play around. Try messing with the initial guess and the costs and see what happens. Because this is like a local thing, right? Local optima, blah, blah, blah. You can actually get different answers out of this if you keep running, because we're using random noise to initialize it, right? So if I run this a bunch of times, you'll get different answers actually because of the randomness, the initial random guess. It'll like end up in different local optima if you run it a handful of times. So if you run this like 10 times, you're going to see some different results, which is kind of interesting. I don't have time to do that now. Go play with it. It's fun. It's cool. You can also, if you play with the cost, you can get different numbers of pumps. If you like put a big cost on the R matrix, it'll like swing up slower because it'll use less control effort. So it'll like pump a few times. So you can get different numbers of pumps out of it. It's super fun. Next time. Catch you guys later.